Okay, so do you remember where we were last time? Dynamic programming. So I introduced to you the basic notion of dynamic programming. I guess I pointed out to you that there is very little in it as such for it to get a name, but it's a good idea. And what we are going to do now is step back and try to attack the same problem that we were attacking before using dynamic programming. Okay? So what we did, we were trying to attack the following problem: single source shortest path. The first set or the first algorithm that we went after was a case where edges have positive weight, and when all edges have positive weight, we introduce something called the Dijkstra's algorithm. And one way of looking at Dijkstra's algorithm was that it is a very smart way to relax every edge exactly once. Okay? And the manner in which we went about doing this was you started with a source and you drew a small circle around it saying that this is the node that I know the shortest path to, and over time what I am going to do is I am slowly going to expand the set of nodes that I know the shortest path to, and that was the set that we said was the capital S. The remaining was sitting in a priority queue, and every time we picked a node from the priority queue which had the smallest d value and put it in, and then relaxed the edges for that particular d value. And the proof essentially was that if you pull the guy who has the smallest d value, you are guaranteed to get a node for which that is the shortest distance. And the manner in which we went about proving it was we said, let this be the source node, let this be the next guy that is being pulled, but for some reason it is not a node for which we have already hit the shortest path. And then the argument went about saying that let us say that that is the shortest path, and we are going to look at this edge where you leave the set S for the first time. And then we said that, okay, based on all the data that we have, all the information that we have, we can show that the d value of this is going to be smaller than that. Okay? And so it needs to be pulled in. Now, the entire argument was based on this being on the shortest path and therefore having a shortest path distance less than the shortest path distance of this. Okay? Now, look what happens if you suddenly take an edge and make it a negative weighted edge. If you have a negative weighted edge on the shortest path, there is no guarantee now that the shortest path length to this is going to be greater than or equal to the shortest path length to this one. And the reason for that is that you might have risen to a certain amount of distance, and then you go about this, and then boom, you have a huge drop, and so the shortest path of this node is actually shorter than this one, and that breaks Dijkstra. So if you have negative edges, Dijkstra breaks, and so the question is, what do you do when some edges are negative? And I argued to you that even if you have negative weighted edges, you can still have shortest paths, except the case where you have a negative weighted cycle. If you have a negative weighted cycle, then you cannot have a shortest path simply because you go through the cycle one time and you actually drop your weight. So you can go through it multiple times and keep dropping your weight until you become minus infinity. Apart from that, you can always get a shortest path. Okay? So our goal previously was to attack this problem. We are very clear about the fact that we cannot go about doing it like Dijkstra does it. Dijkstra goes and essentially relaxes every edge exactly once through the entire cycle. Having said that, I set that on the side and said, let us look at something called dynamic programming, and then explain to you exactly what dynamic programming is. Okay? And essentially the point was the following: you take your problem and see whether you can come up with a recursive solution. By a recursive solution, you simply mean give me a problem such that if I have the solutions to the sub-problem, I can build the solution to the problem itself. Okay, all of you know what recursion is. But this notion of a problem and a sub-problem immediately means that you are looking for some kind of index. In the simplest case, it is going to be a linear index. Okay. Sometimes you can have several sub-problems and you can have a recursion which is based on trees, but in simpler cases, you are always looking for an index based on which you can say that if I have this problem with index 25, in order to solve it, I need a solution to this index with value 24, maybe 23, and I can put them together to produce the solution for index 25. So, you are always looking for an index. As soon as you get a notion of an index, you then write down the recursive solution for your problem. Once you write down the recursive solution for your problem, you have two ways to go. Okay. One is essentially exactly replicate it in your code, which is essentially going to run based on recursion. It is going to make recursive calls, or you look at this and say, it looks like this recursive solution seems to be solving several problems over and over again. If that is the case, the immediate thing that you should do is solve a sub-problem just once, store the value. An even easier way to do this is to essentially build the problem from the bottom. Okay, and that was what dynamic programming is all about. So, I am now going to try to solve this problem using dynamic programming, and you will see how the solution pans out, and then we will go back to something called Bellman-Ford. Okay. So, we are looking at the same problem. You have a graph, it is directed, okay, has edges with weight, and some weights are negative. Okay, so, I am saying undirected simply because you can have edges going the other way too, in which case you say, so if you are given a graph which is undirected, then you have forward looking edges and backward looking edges. But the basic problem is the same. So, you have a directed graph, you have every node from which there are a bunch of edges going out, you have weights sitting on them, and there is a possibility that some of these weights are going to be negative. And you are looking for the shortest path from the source. And as such, it looks once again like a graph theoretic problem. You might be thinking about it from a traversal point of view. Right. So, you are given graph theoretic problem, you start thinking about how it is that I can start from the source and somehow find a way of traversing the entire graph in order to get my solution. That is typically the way your mind works. But when you are looking at a problem from a dynamic programming point of view, you have to flip this whole view of things. So, in this particular case, soon as you think that there might be a dynamic programming solution, what you are looking for initially is an index. Some index based on which I can write a recursive solution to this. Can you think of anything? Okay, what I am trying to do is, rather than give you the solution, I am trying to sort of think about the path via which we arrive at a solution out here. I am looking for the values of the following. So, d underscore I in my case is going to be the shortest path distance from the source to node I. Okay, it is going to turn out to be a number. However, just saying that I want to solve the entire problem, get all the di's, is not allowing me to think in a recursive manner. For me to be able to think of a solution for this in a recursive manner, I need an index. I need to know which is a bigger problem, which is a smaller problem. How I can take a big problem and say that its correct solution depends upon solutions to sub-problems. Sub-problems meaning the problem with a smaller index. I have to produce an index in my head. Somehow, I want to start with a solution which is not only di, but also refers to something else. In this particular case, it is very unlikely that you can immediately get to it because you have been introduced to dynamic programming for the first time. Okay, but let me tell you what it is, and then you will immediately be able to see that yes, that could be a good index. Index I am going to use is the length of the path, number of edges. Okay, so this is a very important thing. You cannot just simply say I am going to use dynamic programming. The thing that you need to resolve in your head when you think that you might be able to get a dynamic programming solution to a problem, the first thing you have to think about, and the only thing that is actually difficult to come up with, is this thing, the index. Okay. In this particular case, if you think about it a little, you will see that there are very few choices given to you, and then you might be able to fall upon this as an index. What do I mean by this? What I mean is simply the following. I am not looking for this. Okay. This to me is going to be the final solution. What I am looking for is this, by which I mean what is the shortest path from the source to node I that has at most k links in it, k edges in the path. Okay, so I have slightly changed the problem. Instead of saying give me the solution, which would be the single shot solution that you always think of, traversal, you will traverse the whole graph, you will figure the whole thing out in one shot. Instead I am saying now think of problems and subproblems. Is there a way for you to take the bigger problem and say that if I had solutions to subproblems, I would be able to solve this? In this particular case, I am claiming that this thing, which is essentially the distance of node I from the source, that is only allowed k hops, by which I mean that the path has only k edges, has a recursive solution. Before that, I want to ask you, so what is di? The final di, what would that be? So, is there some value of k for which d, so of course, k can be infinite, right? You are allowing infinite number of edges, and therefore, it is the correct solution. Is there some smaller value of k that you can allow for which dik will become the answer? Number of vertices minus 1. Does that make sense to people? I am claiming that if k is allowed to be number of vertices minus 1, then you will have di, by which I mean that the shortest path can never take more than number of vertices hops. If it did, it essentially means that it went through the same node twice, someplace, by which I mean that there is a cycle. And very clearly we know that cycles are not negative weighted, at least that is the assumption currently, and so your shortest path is not going to go through the same node more than once. And therefore, if we simply allowed k to rise all the way till v or v minus 1, v meaning the number of vertices, I have the answer. Agreed? How many here do not understand that? Okay, good. So, I know that if k is that many, I am pretty much done. Okay, so, I am just simply going to start with v minus 1, and I want to have the solution for v minus 2, have the solution for v minus 3, and so on and so forth. Here is my second question to you. Can you think of how you can relate this to smaller subproblems? This, in my opinion, or this, the way we have defined things, are sub-problems, by which I mean I am reducing the index. So, this one basically says the shortest path distance from the source to node something j, which has k minus 1, at most k minus 1 jumps to it. This one is the shortest path distance of somebody out there, which has at most k minus 2 jumps to it, and so on and so forth. What I want is to write this in terms of those. What is the shortest path distance from a source node to any given node, which has at most length of k? If I knew the shortest path distances to all nodes with lengths at most k minus 1 or k minus 2 and so on and so forth, do you think I could solve this problem with at most k? Yeah. Yes, you are thinking right now. You are basically saying that, okay, if I have all these solutions, there are two possibilities. One is the shortest path distance to that node of length at most k is the shortest path distance of length at most k minus 1 itself, or using some path of shortest path distance k minus 1, you end up someplace and then you make a final hop there. Right? This is a recursive solution. It comes as a second thing that comes to your mind. The first thing is you have to look for an index. The second is you have to figure this recursive solution out. There is nothing called dynamic programming really. All that you are doing is solving the problem like I am saying you have to solve it. You have to come up with some kind of an index. You have to come up with a recursive solution. Once that is done, the rest is just obvious. Okay, so here is what my claim is. So my claim is that the I k is the minimum of the I k minus 1 and okay. So, I am claiming that the shortest path distance to node I, starting with the source node of length at most k, is the minimum of this being a large set and this being a smaller set. This one is just coming all the way to I using just k minus 1. So, allowing yourself one more hop does not make your shortest path any shorter. Okay. For example, think about a source node which in 3 hops gets you to the correct answer. So, allowing yourself 4 hops or 5 hops or 6 hops does not reduce the shortest length distance. That is one possibility. The other possibility is the shortest path distance from the source to node j with at most k minus 1 hops. Once you have come to j, you now take a final jump to I using wji. So, here is I, these are nodes which are j. From the source node, you come to any one of these and then you make the final jump. Okay. So, that is at most length k minus 1 plus 1. So, at most length k. Agreed? Okay. Does it change the solution if you went k minus 2? Why is it that I am claiming that just k minus 1 is all that we need? Why do I not need to use a solution to k minus 2? Yeah. If you did your k minus, let us say that I try to write the solution with k minus 2, right. I would come someplace k minus 2, I would need 2 more jumps, but the first jump would take me to k minus 1, for which I already have the solution recorded. So, I do not need to refer to k minus 2 anymore. What I am doing is I am first of all proving to you that this is the correct answer. Okay. Right now, your job is to understand that this is the correct answer. I am just giving you a proof that this will give you the correct answer. The shortest path distance to any node is with some number of hops is the shortest path to that node with lesser hops or lesser hops someplace else and then a jump. Okay. So, here yes. How about this? I can remove this by saying Wii is 0, which is true. If I set up in my graph Wii is 0, meaning that the time it takes to go from I to I or the length of the path from I to I is actually 0, then I can take this piece out completely. You can clearly see this is essentially dik minus 1 plus Wii. If you replace the I with a j here, that is essentially what I am talking about. So, I can take this completely out and allow for j to also be I. So, in this particular case, I am saying j not equal to I. So, here is a solution, or if j is allowed to be I do not need this piece. Does that answer your question? Yeah. Why do I need which one? The first piece? Okay, so that is why I am saying if it is through other, see remember, if there is a path from source to a node I, which is the shortest path and is of length 3, okay, and I ask you what is the shortest path from the source to node I, which is of length 4 or less. You will not add any edges to the path. So, you will say okay, I will take 3 hops and get to I and then I will stay there, hop again to itself, hop again to itself. So, these are the empty edges that I am trying to use up. For a solution which is 4 or less, where the solution is already 3, you will take that path and then you will stay there. Okay. This is the peculiarity of the index itself. You see, the index is forcing you to think about the solution slightly differently. Without the index, none of this would be the case. Okay. Dijkstra never thought of an index. Dijkstra just went and solved the problem in a single shot. Here, we are thinking of an index that is causing us to reevaluate the problem itself. 4 or less, 3 is still 4 or less. So, the shortest path will remain the same. So, di 4 or less will be just di 3. Is that making sense? Any other questions? Okay. So, you have come up with an index, you have written your recursive solution. There is nothing dynamic programming yet. The last piece, which turns out to be dynamic programming, is something that even your much younger brother or sister will be able to do, which is essentially say that I am going to solve this problem bottom up. Once you solve a problem bottom up, you are guaranteed that you are not going to resolve sub problems, so long as you store them in some particular array, and that is all that happens. Dynamic programming solves problems bottom up and just keeps them in an array. So, in this particular case, what is my array going to be? Well, it is a one dimensional array. These are the D's. Okay, so, starting from location 1 all the way to n, I am going to set k equal to 0, or we can always start with k equal to 1. In fact, we should not solve with k equal to 1. So, let us start with 0. So, no jumps allowed. What is going to be your solution? You have to always start your base case out. You are not allowed any jumps, you have a source node, you have all the nodes out there. What is the shortest path distance from the source node to any node in your graph which allows 0 or less hops? What is the shortest path distance from your source node to any node I out there which allows you 0 or less, which allows you no hops? It is infinite, right, because you cannot even get there with 0 or less hops. So, you are going to set everything up with infinites. What about the source node itself? 0. Okay, so you simply set this thing up, and that is your k equal to 0, and at the next step you will solve for k equal to 1. Okay, so you can clearly see I am just going to plug this formula in there. To solve for k equal to 1, you have the k equal to 0 solutions here, and you are just going to say I am going to check the minimum of this value plus the jump value, which is the Wji. Okay? Very clearly what you will have is a matrix of length V that gives you the Wji, the weights of edges from j to I. Agreed? And so you will plug this back in there. In fact, you will write the code so as to have just this thing written out in your favorite programming language, and you will solve it for k equal to 1. This one is telling you how to get di 1 given di zeros. Repeat that. So, after what k will d values not change? How long do you need to run this loop? The next time around you are going to do k equal to 2 and so on and so forth. When will you stop? V. You will run this cycle V times, and that is it. So, order VQ. Why do I say order VQ? If you look at this, every time what do? I am taking a min of something, min of the value already there. Okay, so I am trying to fill this value in. I am going to look at this value, and I am going to look at all of these values, and the Wji jumps to them. Do you see that? In order to fill up this value, so dki, I am looking at dk minus 1I with a jump of 0, assuming that the diagonal values are all zeros. Okay, then I do not even need to separate out the cases. I will essentially just scan through all of these, and each time I will add to it whatever value is there, I will add to it the weight from there to this, and if it is smaller than that, I will change it to that. That is how you write a minimization code. Right. So, you are trying to look for the minimum in an array. What do? You pick up the first element and say I am claiming this is the minimum. Next guy, if it is smaller, then you change it until in the end you have the correct answer. Agreed? Question? No. There is a reason why I am talking about this. I am trying to write code to solve for this. And I am claiming that the way I am going to solve for this is, if I want to find the answer to this, I essentially am going to scan through this entire array, take the value that is already there, add to it the weight from that node to that node, and if it turns out to be smaller than this, I am going to put it there. I will go to the next one, I will go to the next one, and so on and so forth. And whenever I find that I am finding a sum which is smaller, I am going to replace it. And I go all the way to the end, and I have the solution for that. What is the length of the scan? V, right? For every node, I have to scan the entire thing. So, this jump, what is the complexity? And this length is again V. So, this is an order VQ algorithm. Great. but there is something else, which is I want you to tell me what am I doing. I am starting, so I am doing from k equal to 0 to k equal to 1, or maybe from k equal to 5 to k equal to 6, but I am doing the same thing over and over again. To find the value here, what I am doing is I am taking this value, adding to it the weight of the edge and seeing whether it is smaller than that. If so, I am going to change that value to that smaller value. I then go to the next one, next one, next one, and so on and so forth. I scan through all of them. Do you see what I am doing? With respect, let me explain my question to you a little better. I am claiming that there is something we have done before, which we gave a name, which is essentially what I am doing. We gave this particular process a name. You just cannot see it right now. What am I doing? I have a d value that I need to fix. I take the first d value, add to it this edge length, and change it if this edge length plus this d value is smaller than that. Relax. So, what is this algorithm basically doing? Relax, 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 relax. You got a value. Do it for this one, scan through the entire thing, relax, you got a value there, again relax, got a value there, and so on and so forth. Do you see that? Changing this value by this value plus this weight is essentially relaxing this particular edge for the value d here and the value d here. So, right now if you take out the indices and just have those d values sitting there, then that edge is essentially being relaxed with respect to those two d values. Is that clear? How many do not get it? How many get it? Okay. So, if I were to store this thing in this form in an array, okay, then I will not talk about relaxation. I will essentially talk about dij's coming with the wji's. It would be a matrix version of the problem. But we essentially know that if I were to see this problem slightly differently, all I am doing is relaxing all the edges, then again relaxing all the edges, and so on and so forth. Every relaxation is one full scan. That is my claim. Why is that? A single scan, where previously I was saying we were v square, I am now claiming is just E. I relax all edges. The difference I am trying to point out is the following. In the previous version of things, I want the correct value for this. I scan through all these vertices and take the d values, add them to their w values, and change that. And I do that for every node. That is one version of things. That is a node centric view of things. That is a vertex centric view of things. The edge centric view of things to me is that I want to go from this stage to this stage. I have all the d values sitting here. I just simply go and relax every edge, and I claim that what I have just done is exactly the same thing as this one. Do you agree? I simply go and relax all edges. How many here do not see that they are the same thing? How many here see that they are the same thing? Okay. So, you clearly know the reason I am saying that this is the case is because the wji, the I is going to be fixed for this one, and so j whatever it be, that I on the right side is never going to repeat. So, essentially when you do this minimization procedure, you are hitting every edge exactly once, not more than that. You do not relax the same edge here once and here once. It does not happen because the I has changed. When you are working out here, the I is different, and that is why we can simply say that you relax all edges. So, Bellman-Ford, for people who are not dynamic program centric, is an algorithm that does not at all look like dynamic programming. Okay? Here is Bellman-Ford. Of course, the Bellman of Bellman-Ford is a person who came up with dynamic programming. He did not want to impose dynamic programming on people. So, here is an algorithm that is written, which clearly does not look like dynamic programming, but now you know it is dynamic programming. So, sometimes an algorithm will not look like dynamic programming. Essentially, what this one says is that we have seen the solution, and therefore, we know that all you need to do is relax all edges, again relax all edges, again relax all edges, again relax all edges, and do this v minus 1 times. That is all that is happening. So, you initialize your d values to infinite if you are not the source, and your d value to 0 if you are the source, and then for I equal to 1 through the number of vertices minus 1, which is the number of times you have to relax, because k can at most be v minus 1 or v. For each edge, relax. Okay, so, previously that algorithm was order v cube, but in this case if E is smaller than v square, if it is a sparse graph, then by simply hitting all edges you have probably reduced your complexity. Okay, so, rather than saying order v square, E can be at most v square, but E can be much less than v square, in which case this is a more efficient algorithm. There is one final piece that Bellman-Ford does, which says here is the strength of Bellman-Ford. Okay, remember I said that if you have negative edges, you can still have a solution, except that if you have negative edges with a cycle, then you cannot have a solution, because you can go through the cycle more than one time and keep dropping your d values. So, Bellman-Ford not only gives you the correct answer, it does a last step, and in the last step all it does is says go and check and see whether you can relax one more time. So, this one is essentially saying for each edge, if dv is still greater than du plus the jump, right, for that edge, if dv is still greater than du plus this jump, meaning that I can relax that one more time, I can drop the value. That is all it is saying. If I can go for every edge and if I can go and drop the value, if I can relax it, if I am successful in relaxing it, then just come and say false. By false, you mean that I have found a negative cycle. So, Bellman-Ford does not have to go and look for negative cycles. It just says I will run it v minus 1 times, I will relax it. I am guaranteed that that is the correct answer, or if I can relax one more time, I will say that there is no possible answer. Then I will be able to keep going for infinite time. This is Bellman-Ford. Okay, this is the version that we usually teach if we do not introduce dynamic programming first. So, if it were the case that I did Dijkstra, I did not talk about dynamic programming, I would have to approach this whole problem very differently, saying that I am going to relax all edges, I am going to relax all edges, I am going to relax all edges, and so on and so forth, and I will do it v times. Whatever I get, I claim will be the correct answer. I will try one more time, and if I can still relax it, then I claim that there is a negative cycle, and so I will return false. We know this is correct simply because of that argument that I already made to you, but assume that I did not come to you with a dynamic programming point of view, in which case I would have to prove the correctness of this algorithm. So, let me give you the proof of correctness of this algorithm where we do not discuss dynamic programming at all. Okay, so, here is my proof of correctness. Mind you, the proof of correctness here was you being able to argue that your recursive equation is correct. The proof of correctness there will have something to do with relaxation. Okay, so here's a claim. So this is called the path relaxation property, and soon as I describe to you exactly what's happening, you will know that it is the case. So it's basically saying let P be the shortest path. So for some reason, I'm assuming a priori that I know the shortest path. So here is your source node, which I call V0. Here is Vk, and I'm assuming that this E is the shortest path. And I have nodes V1, V2. So I have essentially chosen the shortest path, and I have a bunch of nodes in the middle. Now I'm claiming that let the edges of P be relaxed in the order V0, V1, V1, V2, and so on and so forth. So if I were given the shortest path, then if I were to relax this first, then relax this, and so on and so forth. So mind you, these are all edges now. So if I do the relaxation in that order, so if I relax this first, then this, then that, and so on and so forth, then by the time I am done, I would essentially have the d of Vk being the shortest path from the source to Vk. Let us first take care of that. Do you see why that is the case? If I relax the first edge along the shortest path, right, then the d value of that is essentially going to be the d value of this, which is 0, the d value of the source node, plus this weight. It immediately gets the correct answer, because I am doing it along the shortest path, obviously. The next time around, I am going to relax this. This is already the shortest path. I relax that, that gives me the shortest path to the next node, and so on and so forth. So it is essentially, if I could somehow magically find out what the shortest path is, which unfortunately is what I am looking for anyway, but if I knew the shortest path, the way to go about relaxing is to relax this first, then this, then this, then this, and so on and so forth. By the time I get to the end, I will have my shortest path. This second piece is saying something slightly on the side which allows us to do this. It is basically saying this does not actually get affected if I, during this period, do some other relaxations. So let us assume that this is the shortest path. I relax this edge, and then I go scratch my head and relax a few other edges out there. Maybe even relax some edge in this path itself, but I am still on this thing. See, I am essentially going to relax, 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 and while doing that, I will also do other relaxations. It is essentially saying that if you do other relaxations and if you take them out, it does not matter, which is obvious, right? Because in the end, I am just focusing on these relaxations. What will happen if I relax an edge? The d value will drop slightly, but the true drop to the shortest path distance will happen when I get there and do that final relaxation. So this is saying that you can go about relaxing other people, but you have to keep your mind on the path and do it in this manner. That is all this is claiming. Now, here is how Bellman-Ford is correct. It is claiming that any shortest path cannot be of length greater than v minus 1. So there is a shortest path, and it has to be a particular length. When you go and relax all edges, you will hit the first edge at some point. Assume that to be your hit, and assume the all other hits to be just, you are just relaxing all over the place. Second time around, you are going to relax all edges. Assume that you have just relaxed all edges, except that when you hit this relaxation, you say that, oh, I have done the second piece, and so on and so forth. And because you are relaxing all edges, I can in parallel see this happening for all nodes starting from the source node. Do you see that? I have a source node, I have all these nodes, I have shortest paths to them. You are going to relax all edges. I am going to say, soon as you relax this edge, you say that, okay, from this source node to this, on the shortest path, I have just relaxed. All the other things I do not care about. But the other person who is looking at this other shortest path, that person sees his or her own relaxation to be the correct relaxation and everybody else being the wrong relaxations or the side relaxations. So with a single relaxation, because you have taken care of all edges, every path will get one jump. every path from the source node to some node will get 1 jump. Second time around, every path will get 2 jump. Third time around, every path will get a third jump, and so on and so forth. And because all shortest paths are of length v or less, by the time you have run this thing v many times, you have hit all shortest paths. I could have told you this without introducing to you dynamic programming, but I wanted to give you two different views into this, because Bellman-Ford is not just Bellman and Ford, Bellman is dynamic programming. The idea came about because Bellman knew, understood dynamic programming and used it. Okay. One final piece, why is this the case? Okay. So, I am going to show you that this is going to be the case. If this were the case, then there is a negative cycle, and I will prove it to you by contradiction. So, I am claiming that assume that you have a graph where you have a negative cycle. So, this is V 0, the source, it does not have to be the source. So, you have a V 0 node. So, some place in the graph I have a V 0, a V 1, a V 2, a V 3, so I have a cycle, and my claim is, so this is W 0 to 1, W 1 to 2, and so on and so forth. The summation W I j along the cycle is strictly less than 0. Okay, so, this is a negative cycle. Now, I am claiming that if this were not the case, then I cannot have a negative cycle, and that is actually very easy to see. So, what I am going to do is I am simply going to go with the converse of this. So, I am going to assume that d 1 is actually less than d 0 plus d 1 is less than d 0 plus w 0. Assume that in all cases it is not true. For this particular cycle. So, I am just running through the cycle. I am going to add them all up. What do I get? Do you see that things strike out? V k is actually V 0, and this is going to strike with that. So, when you add all of these up, you are essentially getting summation of weights which is in contradiction with your cycle being a negative weighted cycle. And therefore, if your cycle is negative weighted, it is not possible for this to be the case, and that is essentially what that is saying, that if you can go and relax any edge, you have essentially found a cycle, and that ends Bellman-Ford. Okay, so, here is a proof of Bellman-Ford, which is very different from the dynamic programming point of view. I will take a break, we will come back to all pairs shortest path.